So again, like I said, these are just names for different types of matrices. So here we talk about diagonal matrices, triangular matrices, and symmetric matrices. So each time the book introduces a new name, and then we see an example for each of these types of matrices, and also some properties. So, and all these names are kind of good, I think. So the name already tell you already what we mean by this type of matrix. So we start with diagonal matrix. So the definition for this, a square matrix that has only 0 entries along, oh no, I say better outside the diagonal is called a diagonal matrix. So diagonal matrices can have only non-zero matrices along the diagonal. Everything outside the diagonal has to be 0. So that doesn't mean that along the diagonal there can be no 0. It just means outside the diagonal everything has to be 0. Okay, so that's what we call a diagonal matrix. And we just go over some examples. So I hope that makes it clear. So for example, this thing here, that is a diagonal matrix because with diagonal, I mean always the main diagonal. So A11, A22. So diagonal is always this, and everything outside has to be 0. So that's a diagonal matrix. So the next one, 4 by 4, 6, 0, 0, 0, 0, negative 4, 0, 0, 0, 0, 0, 0, 0, 0, 0, 8. Again, this is the diagonal. Everything outside the diagonal is 0. So this is a diagonal matrix. Even there's a 0, keep in mind this is an 8. This is a 0, it's along the diagonal, but there's no problem. The diagonal can also be 0. The point is everything outside the diagonal has to be 0. What's on the diagonal, we don't know. And then finally, so the most extreme case is this one, 0, 0, 0, 0. This is our diagonal. Everything outside is 0. So the 0 matrix is also a diagonal matrix. It's an extreme case because everything is 0, not just the outside diagonal. Okay, so these are examples of diagonal matrices. Okay, and what is so special about diagonal matrices? First, it's very easy to solve a linear equation system with a diagonal matrix because it says, let's say 6 times W is something, negative 4 times X is something. So diagonal matrices are very easy matrices. So these are the best matrices you can get in some way for a linear equation system. And so, and also when you think about what the Gauss algorithm does, it moves from a general linear equation system to reduced row echelon form. But the part in the reduced row echelon form where we have the leading ones, that's actually diagonal matrix. So the Gauss algorithm essentially tries to achieve that kind of a diagonal matrix. You cannot always do it. That's why we say reduced row echelon form, because it's not guaranteed that you get a diagonal matrix, but the goal is to come close to a diagonal matrix. So diagonal matrices are something good. Once you have a diagonal matrix, everything is easy. For example, solving a linear equation system. And the other thing which you have seen a little bit in some of the homework question It's not really clear why we would do this, but very often in applications, you actually need powers of matrices. Like if A is a matrix, you're looking for A squared, A cubed, A to the power of 4, and so on. And again, and for general matrices, that's very difficult to calculate. Not difficult in the sense that we don't know a formula. We have an easy formula, but the effort to do it, the amount of work is really big. For diagonal matrices, it's not difficult to calculate the power. And that's something I write down now here. So we're talking about powers of diagonal matrices. So let's do a diagonal matrix. So the diagonal elements are just called D1, D2, up to Dn. So this is n by n. And everything else is 0. I mean, I make a big 0 means everything else is 0. No? So for this matrix, if you calculate, like say, this matrix square or this matrix cube means D times D times D, the exponents just go to the diagonal. Nothing else happens. So it's essentially like calculating powers of numbers because all the off-diagonal elements give us a 0. So just this is something I like to write down. So if you calculate, for example, if you have an exponent larger than 0, or I can also make larger or equal to 0, then d to the power of k is just, you take the diagonal elements, d1 to the power of k, t2 to the power of k, up to dn to the power of k, and everything else stays 0. So this is just what happens if you calculate the power of a matrix. And again, you see that's not much work. No, you have n numbers, and each of the numbers you have to take to the power or raise to the power of k. And so that's not more work than doing it for numbers. Where remember, when you do matrix multiplication, in general, you have this sum, and that really costs a lot. So that's why calculating powers of matrices is, even if you use a computer for larger matrices, is a very slow operation. But for diagonal matrix, it's easy. Okay, now you also see if none of these diagonal elements are 0, so if they're all non-zero, we can also use negative powers. So if all diagonal elements are non-zero, I goes from 1 to n, then also for negative exponents, we have d to the power of k in the same way as d1 to the power of k up to dn to the power of k, and outside tons of zeros. And because now we have negative exponent, but this number is non-zero, so we can actually calculate this. Especially we have the inverse in the same way as d1 to the power of -1, and now I write it differently. I just write 1 over d1, 1 over d2, up to 1 over dn. So this is just the inverse. Keep in mind, 1 over d2 is the same as d2 to the power of -1. So this is very nice about diagonal matrices. Powers are easy to calculate. Then the last thing about diagonal matrix is, again, matrix times matrix, again, in general, is difficult in the sense it's a lot of work. Not for the formula. We know the formula exactly. But again, if you take matrix times matrix, and one of the matrices is a diagonal matrix, it turns out it's much faster and also easier to calculate. There's actually not nearly nothing to do if you multiply a matrix with a diagonal matrix, either from the left or from the right. So we write this down. So that is kind of in the moment the last result for diagonal matrix. And I start with an example, and then we write down in general. So I just use an arbitrary matrix. I think it's from the book, 2, 2, 1, 1, 1, 4, 2, 0, 1. So this should be just a random matrix, something for an example. And I multiply it also with a random diagonal matrix from the right. And I use, again, a very simple matrix, 1, 2, 3 along the diagonal. And the question is, what happens if you take an arbitrary matrix, this is just an example, and you multiply it from the right with a diagonal matrix? And again, we have learned now many different ways of how we can look at matrix vector multiplication. So this time I like to do it column by column. So let's look at column 1, 1, 0, 0 times this matrix. And you see 0, 0 always hit these two numbers. So all what happens is 1 is multiplied with the first row. So we get 2, 1, 2. Now we look at the second column, 0, 2, 0. 0 hits always the first column. The last 0 hits the last column. So only the second entry is always multiplied by 2. So we get 4, 2, 0. And now we use the last column, 0, 0, 3. This 0 always goes to the first column. This 0 always goes to the second column, so they don't show up. And then the 3 is multiplied by the last column. So 3, 12, 3. So if you multiply a diagonal matrix from the right, these numbers go to the corresponding columns. So the 1 goes to column 1, the 2 goes to column 2, and the 3 goes to column 3. And that's how we get these matrices. So whenever you have to multiply a matrix by a diagonal matrix from the right, you don't really have to do matrix multiplication. You can distribute each diagonal to the corresponding column. So matrix multiplication with a diagonal matrix from the right is just column multiplication of these certain numbers. Now we flip the two and see what about if we come from the other side. So what about I put this matrix here? Again, our example matrix, same thing. Now we have learned that another way of looking at a matrix vector multiplication is that we can always work from the left matrix, always row by row. Okay, so let's multiply with row 1 to get row 1 here. And we see the 1 goes to the first row and 0, 0 hits the second and third row. Because they're hit by 0, they really don't play a role. It's only this number always multiplied by 1. So it turns out it's 2, 2, 1. Now we look at the second row. Second row tied each column. This 0 hits the first row. This 0 hits the third row. So only the middle row, the second row, is hit by a 2. So it turns out we just take the second row and multiply by 2. And then finally, now you know maybe already what happens. If you look at the third row, 0 is multiplied with the first row. This second 0 with the second row. So essentially that means they don't show up because they are multiplied by 0. Only the 3 goes to the third row. So it turns out you multiply the third row by 3. So the 1 goes to the first, the 2 to the second, and the third to the third row. So multiplying with a diagonal matrix from the left is the same as multiplying every row with the corresponding diagonal element. So again, the lesson is multiplying with a diagonal matrix from the left. You don't have to do matrix multiplication. You just can multiply each row by the corresponding number. So this is something I like to write down. So if we multiply n times n matrix A by a diagonal matrix D, which has entries D1 to Dn along the diagonal from the right. So that was the first example here from the right. Then column J of A is multiplied by dj. And that's true for every j. J goes from 1 to n. If we multiply A by D from the left, then rho j is multiplied by dj, again for every row. Okay, so again, the message is diagonal matrices are easy to work with. No? Easy to solve linear equation system, easy to calculate powers, easy to multiply with other matrices. Okay, so they are the kind of the perfect matrices, but the stupid thing is not often do we actually have some diagonal matrices. But a lot of algorithms in, let's say, in numerical, what's called numerical analysis is an area of mathematics, or also in computer science, when it's about singular value decomposition, eigenvalues, eigenvectors. A lot of these things are targeted to modifying a general matrix to make something which is like a diagonal matrix or equal to a diagonal matrix. So diagonal matrix is always like a goal to reach, but you usually have to do some work to reach the goal. For example, finding eigenvectors and eigenvalues, which you see at the end of this class. And there are other things which you might have heard in other classes. And in some way, as I mentioned in the beginning, the reduced row echelon form is also kind of a step in this direction. Even the reduced row echelon form is not necessarily diagonal matrix. And the reason is we cannot always reach the goal. So sometimes the reduced row echelon form is the best we can get. Okay, so that was the first new term. When I say in the future diagonal matrix, we know what we mean by this.